Hello and welcome to this presentation on concurrent forces using analytical solutions. This presentation builds on a previous presentation related to concurrent forces where we use graphical methods to produce our solutions. It is assumed you have seen the previous presentation as some of the terminology and definitions outlined in that presentation underpin this presentation. Because we're involved with analytical solutions, it is assumed you are familiar with Pythagoras' theorem and also the use of the basic trig functions sine, cosine and tangent. If you need a recap on Pythagoras' theorem or basic trig, please review separate presentations on those two topics. An example of a typical solution in this presentation, we may be given a resultant force of 10 kilonewtons and need to resolve it into its horizontal and vertical components. But unlike the previous presentation where we use graphical methods to solve these problems, here we'll be using basic trig functions to evaluate our answers. In other instances, we'll be given the actual components, the fx and the fy. We'll have to solve for the resultant force. So in the previous presentation, using graphical methods, we were undertaking resolution of forces. It was shown that two or more forces or vectors can be combined into a single resultant force using a force vector diagram. So from the previous presentation, we were given a system of forces. There are 5 forces here labelled FA through to FE. And we could construct a force polygon to a particular scale that we chose, and we could draw the 5 forces head to tail, producing what's called a force polygon. And from the beginning of the polygon to the end of the polygon, define the resultant force and its direction. So we could define the force by measuring its length to our scale and also measuring the angle theta with a protractor. So that's the graphical method as outlined in a previous presentation for finding the resultant force. Now, as an alternative, a single vector can be replaced by other vectors which have the same combined effect. So when a single vector is replaced by 2 or more components, it is said to have been resolved into components. So in the little sketch here, if we were given a resultant force, I've labelled it as F suffix R here, of 5 newtons, we could resolve this force into horizontal component here, Fx, and a vertical component shown here, labelled Fy. So these two components, the Fx and the Fy, are represented as a right-angled triangle. Such a process can often simplify the solution to engineering problems, especially when the single force is resolved into its two components, which are mutually at 90 degrees to each other, as will be undertaken in this presentation. As mentioned at the start of the presentation, we need to calculate forces here. It's an analytical method. So we'll be using the following mathematical techniques. Firstly, Pythagoras' theorem, which of course only relates to right-angled triangles. Pythagoras' theorem states that c squared, c is the hypotenuse of a right-angled triangle, is equal to the sum of the squares of the other two sides, so a squared plus b squared, using notation shown in our sketch. We will also be using basic trigonometry. Again, that only applies to right-angled triangles. Shown a similar right-angled triangle here as shown on the previous slide. Notice that the angles are labelled as capital A, capital B, capital C, and the opposite sides are labelled with lowercase letters. So this is angle C here, then opposite angle C will be lowercase c, which is hypotenuse in this case. If we were given angle theta here, then opposite angle theta would be the opposite side, labelled as B here, and opposite angle A would be the adjacent side, labelled as A here. That's a typical notation used. And again, from previous presentation, we mentioned the mnemonic SOHCAHTOA, and that simply defines these three basic trig ratios of sine of the angle theta is B upon C, using notation above. Cosine of angle theta or cos theta is simply A upon C from the notation above. And tangent of theta, tan theta, is B upon A, and again for notation above. And these functions are all programmed into our calculators. We will also need to transpose these to the equations. So if we want to find B from the sine function, we multiply both sides by C, and we can do a similar exercise for finding side length A from the cosine formula. And if we want to find angle theta, we could use the tan function. Theta is equal to the inverse tan of B divided by A. Again, all this work has been covered in a previous presentation, so if you need a recap on use of basic trigonometry, I would encourage you to review that presentation. Example 1. We're asked to calculate the horizontal Fx and the vertical Fy force components given a 10 kilonewton resultant force as shown in the sketch. So here's our 10 kilonewton resultant force drawn. What we have to do is work out the horizontal component shown here, labelled Fx, and the vertical component here, labelled Fy. Of course, we have a right angled triangle here. As with all trig problems, don't forget we have to label our sides. So if we're given an angle 30 degrees here, then this would be the opposite side of the triangle. The hypotenuse is always the longest side opposite the right angle. So that leaves the Fx side here as the adjacent side. So if we want to find the vertical component, first of all, Fy, looking at the notation in the diagram, that's the opposite side we're trying to find. We're given the hypotenuse side and the angle. So from our previous work, that will be the sine function. So sine of angle theta is the opposite side divided by the hypotenuse. If you're unsure which function to use, you can use the SOHCAHTOA mnemonic, and again we outlined how to use that in a previous presentation. Put in the values here. The sine of angle theta, that's sine of 30 degrees, is equal to the opposite side, that's labelled Fy here, and that's divided by the hypotenuse, and that's 10 kilonewtons. Simply transposing to find Fy, we multiply both sides by 10, so Fy is equal to 10 multiplied by the sine of 30 degrees. And using your calculators, making sure they're in degree mode, of course, that's 5 kilonewtons. So the vertical component Fy here is 5 kilonewtons. Just for clarity, I've tried to show you the calculation here on 2 lines. Sometimes students understand the calculations better when I've written it on 2 lines. And then to find the horizontal component, Fx, labelled in the above sketch, we use the cos function. We're trying to find the adjacent side given the hypotenuse side and the angle, so that's the cos function. So cos of angle theta is equal to the adjacent side divided by the hypotenuse. So in this case, that's cos of angle 30 is Fx, the adjacent side, divided by 10 kilonewtons, the hypotenuse. Again, rearranged in a similar way as above, the Fx is equal to 10 multiplied by the cos of angle 30 degrees. And again, evaluated on my calculator, that becomes 8.66 kilonewtons. It's actually a recurring number here. So that's an example of being given a resultant force defined as 10 kilonewtons magnitude and 30 degrees angle. And from that, we're able to work out the components of the resultant force in the x and the y directions. Here's exercise 1 for you to attempt. Very similar kind of problem. We're given the resultant force shown here of 130 newtons, and we're given the angle of 70 degrees. So what you have to do is again work out the Fx, the horizontal component of the resultant force, and the Fy, the vertical component of the resultant force. This involves a very similar process as shown on the previous example, so I'll let you evaluate this on your own, but the answers are shown here in the brackets for fx and fy. I'd encourage you to start the presentation and attempt exercise 1. Example 2. This time we're asked to determine the resultant force, labelled Fr, given two components, the Fx and the Fy as shown. We also need to calculate the angle theta that the resultant force Fr makes with the horizontal. So from the information given, we have to calculate Fr, the resultant force. We need to know its magnitude and its direction, its angle to the horizontal in this case. So we're given the horizontal component labelled Fx here of 40 newtons, drawn here. And we're given the vertical component labelled Fy of 60 newtons, shown here. So first of all, to find the resultant force labelled Fr, we're going to use Pythagoras' theorem. So Fr is equal to the square root of, in brackets we've got Fx squared added to Fy squared. So inserting the values, that's the square root of 40 squared added to 60 squared, all square rooted. That gives a value for Fr of 72.1 newtons. I encourage you to check that on your calculator. We also need to find the angle theta stated in the diagram above. So I'm going to use the tan function for this. So tan of angle theta is the opposite side divided by the adjacent side of our triangle. So we're labeling our triangle with our notation. The opposite side in this case is Fy. So Fy divided by the adjacent side, which is Fx. So it's simply 60 divided by 40, just the value of 1.5. So to find the actual value of theta, we have to take the inverse tangent, sometimes displayed as arctan or tan to -1 of 1.5, and the button push on my calculator, that evaluates to 56.3 degrees. So in summary, our resultant force, Fr in our diagram, is 72.1 newtons, an angle of 56.3 degrees to the horizontal, as shown above. Don't forget, forces are vectors, so we have to specify a magnitude and a direction to define the force. Exercise 2 is very similar to example 2. In this case, we're given two components of a right angled triangle. We've got the Fx component of 120 kilonewtons, drawn here. And we've got the Fy, the vertical component of 70 kilonewtons, shown here. In this case, we've got to find the resultant force labelled Fr, so we need to know the magnitude, that's the length of the line, and also the angle theta. As I said, this is very similar to example 1, so I'd encourage you to stop the presentation and attempt this question using the process on the previous slide. The answer for the resultant force is shown here. This is the magnitude, this is the direction. So this method of resolving a force into its horizontal and vertical components can be used to accurately determine the resultant force when two or more concurrent coplanar forces act on a body. And don't forget, from our previous presentation, concurrent means that the forces' lines of actions all pass through the same point, and coplanar mean they're all in our two-dimensional plane. So exercise 3, we're asked to sketch the directions of the horizontal and the vertical components for each of the forces shown below. Note that these 60 Newton force components are already shown for convenience. So if we were given the 60 Newton force and we have to resolve it into its horizontal and vertical components, then the horizontal component would be this one shown here, and the vertical component would be this one shown here. So this would be Fx and this would be Fy. Some students find it difficult to know the actual senses to show the arrowheads. So sometimes it helps about thinking of walking along the vectors. So if I wanted to get from the origin here to the end of the 60 Newton vector, I could travel by simply walking along the vector from beginning to end. Alternatively, I could walk horizontally along component fx, and I could walk vertically up component fy to get to the same point from the origin. So that defines the direction of fx. In this case, I'm walking left to right, and it defines the direction of fy. In this case, I'm walking up the page. And that's how we get our arrows on our vectors. So if that idea of thinking of walking along the vectors helps you, then I'd encourage you to do that when resolving forces. You need to get the arrow directions correct. And this is where our sign convention comes in for forces. Notice that the horizontal fx components are positive when their sense is from left to right. That's positive. If their senses are right to left, they will be negative. Also, considering the vertical components, notice a sense that's upwards is classified as positive on our diagram, and if the sense of the vertical component is downwards, that would be negative on a diagram. So this is a force sign convention that we'll use throughout this presentation and also in later presentations. What I would encourage you to do is to try and resolve the 50 Newton force, the 40 Newton force and the 70 Newton force into what you think are the x and y components. In other words, the fx force component and the fy force component. So if we now consider the components for the 50 Newton force, I will have my fx component here in this direction. I will have my y component on the end of the fx in this direction. And of course, this is a right angled triangle. So notice this direction now. The 50 Newton force is shown at some angle to the horizontal. It's not given, but we know it's some angle to the horizontal here. So the fx component here would be negative, and the fy component here would be positive. So negative fx component for the 50 Newton force, but a positive y component for the 50 Newton force. If I now consider the 40 Newton force and resolve that into its horizontal component and its vertical component, I find I get a negative horizontal fx component, and in this case a negative vertical fy component, because the component goes down the page. And finally, if I consider the 70 Newton force and I resolve that into its horizontal and its vertical component, so in this case I have a positive horizontal x component but a negative y component. So we need to be very careful when we're resolving a given resultant force into its horizontal fx and its vertical fy components that we get the sense of the component correct, whether it's positive or negative. One incorrect sense and the whole question is effectively wrong. So again, this is our force sign convention we must adhere to throughout all the problems we're going to consider in this presentation. Here's an overview of the procedure we're going to use to find the resultant force for a given system of forces. You will find in the examples that follow we'll be given 2, 3 or even 4 forces within our system that we have to resolve to find the resultant force. So step 1 of this process, we're going to resolve all the forces into right angled triangles as shown on the right hand side sketch here. Noting that the angles are measured to the horizontal in every case. So even if an angle was given to the vertical in the actual question, we will work out the angle to the horizontal always. So this vector here is given as f, the length of it is the magnitude of f, and then the angle theta is the direction. So now we've got a right angled triangle here, and we're going to find the horizontal component, which is of course the adjacent side of the triangle here. So we're going to evaluate this force component, and the formula is the horizontal component, denoted as FH here, is equal to F multiplied by cos of angle theta. In our previous work, we denoted horizontal components as Fx. Next, we will work out the vertical component of our force, shown here, and the formula for that will be Fv is equal to F multiplied by the sine of angle theta. Again, that comes from our basic trig. This is the opposite side of the triangle we're trying to find. On the previous slides, we denoted the vertical components of the force as F suffix y. So we adopt this approach for every force we're given. If we've got 4 forces in our system, we'll have 4 of these right-angled triangles to resolve into horizontal and vertical force components. In step 2 of the process, we're going to summate all the horizontal components. So in notation format, that's summation of the FH's in this diagram. Noting that horizontal force components moving from left to right are positive. That complies with our notation on the previous slides. Then we're going to summate all the vertical force components, in other words, summation of the FV's, to use notation on our diagram. And again, we notice that vertically upward forces are positive, in line with our notation on the previous slide. Once you've summated all the horizontal components of the forces and all the vertical components of the forces, we will then construct another right-angled triangle. This time we'll have the summation of the horizontal forces on the x-axis and the summation of the vertical force on the y-axis. And then in step 3, using Pythagoras theorem, we will find the resultant Fr of the summation of horizontal and summation of vertical force components. So applying Pythagoras theorem, the resultant force for our system will equal to the square root of, in brackets, the summation of all the horizontal forces squared added to the summation of all the vertical forces squared. That will calculate the magnitude of the resultant force, and then using basic trigonometry we can calculate angle theta to the horizontal. So to calculate angle theta we'll use the tan function, so tan of theta is equal to the opposite side of a triangle, so that's the summation of all the vertical force components, divided by the adjacent side of the triangle, that's summation of all the horizontal force components. And of course, don't forget to find the actual angle theta, we need to use the inverse tan function, tan to the minus 1 on our calculator, of the summation of vertical force components divided by the summation of horizontal force components. So that's a brief overview of the procedure we're going to adopt, and in the following examples you'll see how it's applied in practice. Here's example 3. An eye bolt, shown here, resists the pull of 3 wires, as shown in the sketch. We've got to calculate the resultant pull, that's the resultant force, on the eye bolt from these 3 wires. In each of the wires there are 3 forces, so in this first wire here we have 5 kilonewtons. In the second wire shown here, we have 2.5 kilonewtons. And in the third wire shown here, we have 4 kilonewtons. Notice the angle, 45 degrees to the horizontal shown here for the 5 kilonewton force. The 2.5 kilonewton force is purely horizontal, and the 4 kilonewton force is 30 degrees to the horizontal as shown here. Now as long as we always measure our angles to the horizontals as shown here in the diagram, we can always calculate the horizontal force component Fx shown here using the cos function, and we can always calculate the vertical force component shown as Fy here using the sine function. So that's true as long as we always measure our angles to the horizontal. So let's consider initially the 5 kilonewton force shown here. It's at 45 degrees to the horizontal. I've redrawn it here for a little bit of clarity. So as long as my angle is measured to the horizontal, then the Fx component, the horizontal component, is always the cos of the angle. So in this case, the horizontal component will be 5 multiplied by the cos of angle 45 degrees. And on my calculator, typing in 5 multiplied by the cos of 45 degrees is equal to 3.536 kilonewtons. and that's to 4 significant figures. Also, just make sure your calculator is in degree mode when evaluating the cos of 45 degrees. Now again, because the angle we're using is the horizontal, I know my vertical component Fy will be equal to, in this case, the Fx and Fy components are the same. And that approach is the approach we're going to take for all of the questions. We just need to be careful with positive and negative components as and when they arise. And of course, in this particular case, referring back to our sign convention, we know that the Fx and the Fy are in the positive senses. Now, considering the second force in our system, this is 2.5 kilonewtons, which is purely a horizontal force. So I'm going to write by inspection the horizontal component Fx is 2.5. And of course it's in the positive sense, so it's positive 2.5. And as for the vertical component, it's obviously 0 because a purely horizontal force cannot have a component in the vertical sense. So again, I can write this as 0 by inspection. So the horizontal force component Fx in this case will be 4 multiplied by the cos of 30 degrees, which is equal to 3.464 kilonewtons. And again, that's to 4 significant figures. Now we need to be careful with the vertical component. To calculate its magnitude, it will be 4 multiplied by the sine of 30 degrees, but of course it's a negative force component, so we need to be aware of that. So it will be negative 4 multiplied by the sine of 30 degrees. And that's equal to negative 2 kilonewtons. All we're going to do now is summate and find the total of all the Fx components. So we'll add this component to this one to this one. So that gives me a total of 9.5 kilonewtons for the horizontal summation. And then we total up this vertical component, this one, and this one, which summates to 1.536 kilonewtons. So as the summation of the Fx is positive, that means it will be in this sense. So 9.5 kilonewtons from left to right. And as the vertical component summation is positive, that means 1.536 kilonewtons upwards. So here's example 3 continued. I've just clarified the calculation in the table below. Notice I have put in the calculation for the 2.5 kilonewton horizontal force. The angle, of course, would be 0 there, and you can clearly see that the answers are 2.5 kilonewtons in the x direction and 0 in the y direction. So I see no point in actually calculating them. I would just state by inspection it can be seen these values occur. And what I've done next is to take the summation of the x components, 9.5 kilonewtons, and I've drawn it on my triangle here from left to right in a positive sense. So that's the Fx is 9.5 kilonewtons. And on the end of that, I'm drawing the summation of the Fy components of 1.536 kilonewtons, and I'm drawing that vertically up in its positive sense. Fy is 1.536 kilonewtons. So now from the beginning of our right angle triangle shown here, I can draw a line to the end of our triangle to show the resultant force. The length of that vector is its magnitude, and the angle theta from the horizontal is its direction. So on the next slide, we'll evaluate the resultant force Fr. So here's example 3 continued. So to work out the resultant force, the length of this line shown here, we will use Pythagoras' theorem. So the length Fr is equal to the square root of the Fx squared value added to the Fy squared value shown above, the square root of, in brackets, 9.5 squared added to 1.536 squared. So be careful with the calculator uses there, but that should give you a magnitude of 9.62 kilonewtons. So that's the magnitude of Fr calculated, the length of the line. Now using basic trig, I'm using a tan function here. This is our opposite side, so this must be our adjacent side. So using the tan function, tan of the angle theta is the Fy, the opposite side, divided by the Fx, the adjacent side. And to find the actual angle theta, we use the inverse tan function on our calculator. So tan to the negative 1 of, in brackets, 1.536 divided by 9.5 gives a value of 9.18 degrees. So obviously the right angle triangle diagram above is not drawn to scale, but it doesn't matter here because this is an analytical solution. So in summary, the resultant force, denoted Fr, is equal to 9.62 kilonewtons at an angle of 9.18 degrees to the horizontal as shown above. I strongly encourage you to always sketch the vector diagrams without exception to make sure you get the vectors in the right direction. In example 3, the summation of fx and fy's are positive, but in other solutions we review, they might be negative in sense. So in summary, that Fr value that we've calculated there, that one force at that angle, represents the entire system over here of the three forces applied. Applying the Fr is equivalent to applying those three forces simultaneously. Here's some more tutorial examples. This is exercise 4. We're asked to determine the resultant force in its magnitude and direction of the force loading system shown below. So three forces here, 130 newtons at 80 degrees to the horizontal, purely horizontal 150 newtons, and we've got 60 newtons at 30 degrees to the horizontal as shown there. I would encourage you to start the presentation and attempt this exercise. Again, use a tabular approach as we did in the previous example, and see if you can evaluate the resultant force for this loading system. The answers are shown in the bracket here. This is the magnitude and this is the direction. The full work solution is shown on the following slide. Okay, here's exercise 4 as a solution. So for the 150 Newton force, shown here on the diagram, we can see it's purely horizontal. So by inspection, the horizontal component Fx is positive 150, and of course it's 0 in the y direction. Those values can be seen by inspection. Next, considering the 130 Newton force shown here. Notice the angle is 80 degrees to the horizontal. So evaluating the horizontal component Fx, that's 130 multiplied by the cos of 80 degrees, which should be 22.57 newtons. And the vertical component Fy is 130 multiplied by the sine of 80 degrees, that's 128 newtons. Both of those senses are positive. The horizontal component would be in the positive direction and the vertical component would be in the positive direction. And the third force we're given is the 60 newtons shown here at 30 degrees to the horizontal. I've shown a resolved diagram here just to try and indicate the directions of the various components. We can clearly see that the Fx component will be negative and so will the Fy component be negative to our sign convention. For the 60 Newton force, you can see we've got negative 60 multiplied by the cos of 30 degrees. That gives negative 51.96 newtons. And for the Fy component, we have negative 60 multiplied by the sine of 30 degrees. That gives us negative 30 newtons. So be careful, those negatives we had to add in to the solution. Okay, be very careful. We had to think through the directions of the components in line with the sign convention we're using. So summating Fx's, we get 120.61 newtons, positive sense there. So that means it will be going in this direction. And summating our vertical components, summation Fy is 98 newtons. Again, we've got positive here, so that means the summation is vertically upwards. Exercise 4 continued. So now we're going to draw the two components into a right angled triangle as shown below. So Fx was the summation of our horizontal components, 120.61 newtons. And the summation of our vertical components Fy is 98. So again, I'm drawing a small vector diagram here, starting with my Fx summation, drawing that horizontally, and adding on the end of that the summation of the Fy components. to again produce the resultant force from beginning to the end of the diagram. Gives us the magnitude and the direction. The calculation of resultant force using Pythagoras theorem is shown here. So Fr is equal to 155.4 newtons. And using basic trig, we can find the angle theta to the horizontal, and that evaluates to 39.1 degrees. That's exactly the same process we saw in the previous example, just different figures here. I'd encourage you to stop the presentation and just work through that slide to make sure you clearly understand how the resultant force magnitudes have been found, shown here. Now the angle to the horizontal has been found, shown here. Just for completeness, I've written the resultant force in terms of its magnitude and direction here. Here's another exercise, exercise 5. Again, we're asked to work out the resultant and also the equilibrant force. We mentioned that in a previous presentation for the system of loads applied to what's termed a gusset plate, shown in the figure below. We've got to state the angle of application from the horizontal. Again, referring to previous terminology, these are coplanar forces because they're in the two-dimensional plane, and they're all concurrent forces because their lines of action all go through the same point here. Just be careful of directions. The 80 kilonewtons is shown in this direction here, inward to the gusset plate. Also the 60 kilonewton force is shown inward towards the gusset plate, but the 100 kilonewton force is shown pulling away from the gusset plate, and so is the 40 kilonewton force showing pulling away from the gusset plate. Just be careful of the senses there. And just a little starting point for you, I've just shown you how to resolve the 80 kilonewton force into its horizontal and vertical components. Notice that the horizontal and the vertical components are negative to our sign convention, so be aware of that. So I'd encourage you to stop the presentation and try and attempt this question using the same approach as we used in the previous examples and exercises, just that you've got 4 forces here and not 3 forces, and the answers are shown in the brackets at the bottom of the slide. The full work solution is shown on the following slides. So here's exercise 5. 4 forces applied, 80 newtons, 60 newtons, 100 newtons and 40 newtons. And we resolve them into the horizontal components called Fx here, which totals down here to negative 129.9 kilonewtons. And we've got the vertical components, the Fy components, which totals to 33.75 kilonewtons positive. So just be aware when we construct our right-angled vector diagram here that the Fx summation in this particular case is drawn in the negative sense. On the end of that we draw the summation of the Fy components, the vertical components, and that's in a positive sense. And then this is our resultant force vector, shown in red. This is always drawn from the beginning to the end of the vector diagram to get the sense of the resultant force Fr. What we need to do still is to work out what the magnitude of Fr is and also work out the angle theta to the horizontal. That's undertaken on the following slide. So using Pythagoras' theorem, we work out the value of Fr, the resultant force, given here. And using basic trig, we work out the value of angle theta, which is shown here. Again, we should conclude by writing the resultant force down, the Fr force, in terms of its magnitude and its direction, in this case from the horizontal. And finally, exercise 5 required us to state the equilibrant force, and from our previous work we know the equilibrant force is equal and opposite to the resultant force, so in this case the arrow for the equilibrium is shown in this direction. It has the same magnitude but opposite direction. I'll leave you with some tutorial questions to undertake at your own pace. This is question 1. We're asked to calculate the horizontal and vertical components of the following 5 vectors. Vectors A, B, C, D and E shown here. So resolve the forces in terms of their Fx and Fy and state the values in terms of our sign convention that we defined on an earlier slide. Answers to questions 1a through to questions 1e are shown here. Question 2, we've got 4 coplanar and concurrent forces act at point O on our diagram. The values and the directions of the forces are shown. We've got to calculate the value, the magnitude, and the direction of the resultant force for this system of forces. Again, I would encourage you to use the tabular method we've shown before with 4 forces in the table and resolve them into the Fx, Fy components, and then eventually find the resultant force. The answer is shown here in the brackets. Question 3, we're asked to find the resultant force of the system shown below, which are coplanar and concurrent forces, with angles measured from the reference plane shown here. The resultant force in terms of magnitude and direction are shown in the brackets here. Here's a bibliography used to help generate this presentation. Some very good mechanical engineering and structural mechanics textbooks. I hope this presentation has been of use to you, and thank you for viewing.